Section 1.5 is titled Infinite Limits. And we're going to start out with what that means. Let f be a function that is defined at every real number in some open interval containing c, except possibly at c itself. The statement, the limit as x approaches c of f of x equals infinity, means that for every m value greater than 0, there exists a delta value greater than 0, such that f of x is greater than m whenever the x value is within delta of c. We could make a similar statement for n less than 0. So fill in the gaps, and then again, a picture will explain a lot more than the language actually does for us. This should feel similar to something you've seen before, though, this definition, right? You got a delta in there, right? You got absolute values of things. Should look a lot like the limit definition you saw before, except you don't see an epsilon, do you? You got this capital M thing going on, and that somehow makes things different. And it does. That's what leads us into the infinite limit part of this. All right, so we're going to draw a picture. Go ahead and sketch this picture. And we recognize that in the middle there's an asymptote, right? You all good with that? So right through here somewhere, that asymptote, that's the c value that the problem is referencing up here, an interval containing c except not possibly at c itself. We might not be defined at c itself. Okay, so that's what it's talking about. All right, what this problem or this definition is saying is that any value you pick that's greater than 0, we'll say it's right here, m. If I take a horizontal line and sort of extend it across like this, there's still portions of my graph that are blue that are above that vertical or that horizontal line. That's all this really says. There's no cap. There's no place where I can say it stops. Okay? Now, where is this delta business coming in? Well, the delta is actually telling you right here, how far away are you when you have this length. Okay? It's where the blue actually intersected that dotted red line that I drew across there, the m value. It's where it intersected the m value. That's how far away you are from c. Okay? Remember, this notation means it's a distance. You're less than delta away from the actual c value. Okay? So if we were taking the limit of this function, and this function is called f of x, as x approaches c, and we'll just talk about it from the left for the moment so that we can think about just the left-hand side. As we are moving from the left-hand side towards the x value of c, there's no cap on how high we can go. Okay? Now, be sure and note that the equal sign where it says limit doesn't really mean the limit equals something. Limit is supposed to be a numerical value, and infinity is not a numerical value, right? It's this concept of something being unbounded. Okay? So this actually tells you exactly how the limit fails to exist. The other failure to exist, do you remember when we've had limits before that failed to exist? What was the way in which they failed to exist? So asymptotes this is an asymptote. What else happened that limits failed to exist? A hole. The limits actually exist if there's only a hole. A jump. So if we have the graph coming at two directions and they're actually approaching values and the values are different, right? That's a very different image than this. Okay? So this information, by allowing us to say that the limit equals infinity, that really just tells us how it's failing. Because if we put does not exist on everything, we wouldn't know, it wouldn't give us as much information. So this gives us more information about how it fails. Okay? All right, so we're going to do an example. We're going to determine whether f of x approaches infinity or negative infinity as x approaches 4 from the left and from the right. So what we're going to do is we're going to find two one-sided limits. And we can do this in a number of ways. We can do it from a graph, or we can do it from a numerical point of view, like plugging numbers into our calculator. Okay? We can't plug in 4 though, right? What's going to happen if we try? We get a 0 in the denominator because that's the asymptote that's occurring, right? So we can't do an algebraic approach where we just plug the number in. All right, so what we're going to do is we're going to find the limit as x approaches 4 from the left of -1 over x minus 4. And we're going to do the limit as x approaches 4 from the right of -1 over x minus 4. And it doesn't matter to me how we do it, whether we do it from a graph or from a number, numerical input or a table. But whichever one we do, we're going to write it down so that we verify that we've actually checked it in one way or the other. So what would you guys like to do? Would you like to look at a graph or would you like to look at a table? We'll have more opportunities to look at other things later, so don't everybody answer all at once. You want to look at a graph? Thank you so much. All right, we're going to look at a graph. Okay, so grab your calculator. Go ahead and put in the equation -1 over x minus 4. And we're going to look at a graph. We know there's an asymptote at x equal 4, right? Because that's where the denominator equals 0. And we're going to talk more about that aspect here in just a moment. But we're going to have a dotted line going on over here. What we really want to know is we really want to know that as we get close to the dotted line from the left, does our graph go unbounded vertically up or unbounded vertically down? That's what we're looking for. So as you take a look at your graph, what's going on the left-hand side? Are we above the x-axis or are we below the x-axis? We are above. That's correct. So the graph does something like this. And again, it's a sketch. I don't even really care if it crossed the y-axis in the right spot at all. I don't care about that. I care about what's happening near that asymptote. How about on the right-hand side? Are we above the x-axis or are we below? We're below. That's correct as well. Again, I don't care really what's happening on this graph beyond the values that are sort of near my dotted red line. Okay, so looking at this then, if we're approaching 4 from the left, we are on the left-hand side of 4, we're over here, and we are going toward the x value of 4. Are we approaching infinity or negative infinity? It's infinity. What about over here on the right-hand side? We're supposed to be approaching x equal 4, but from the right, so we're going this direction. Infinity or negative infinity? Negative infinity. Okay. Graphs are great. The thing that you might run into if you try graphs on some of these is you might have to change your window, right? Sometimes just the window doesn't work out. You might have to zoom in or zoom out or change the x minimum, x maximum, those kinds of things until you see what it is you're looking for. Again, don't be terribly concerned about what's happening sort of on the far left-hand side or the far right-hand side of the graph. You're caring what's happening in the middle of the graph wherever this sort of change in behavior is occurring, right? This asymptote. All right, so we've been talking about asymptotes. All of these are occurring sort of around these vertical asymptotes. So a vertical line is a line that goes straight up and down, right? So if f of x approaches infinity or negative infinity, as x approaches c from the left or from the right, then the line x equals c is called a vertical asymptote of the graph. Right? That's what we keep saying. You know that from an algebra course, probably several algebra courses. You've seen this occur over and over again. Okay? So how do we find vertical asymptotes then? Let's say that you have a function, two functions, f and g, and that are continuous on an open interval containing c. As long as f of c does not equal 0, and g of c has a place where it does equal 0, so it's equal to 0 at c, then there exists, I didn't get that typo fixed. I saw it, I think I fixed it on your notes at some point, but it may have been before y'all printed it out. There exists an open interval containing c such that g of x does not equal 0 for all x not equal to c in the interval. The graph of the function has a vertical asymptote at x equals c. Okay? So it's all occurring about the denominator, g of x not equal to 0, g of x is equal to 0. So at this one value of c, the denominator equals 0, or maybe 2 or 3 values of c, but it's a specific number of them. It's not infinitely many. Okay? So we have specific places where this equals 0, not the whole number line. I should say it that way. G of c is not the equation 0. There's specific places where it equals 0. Everywhere else, you're good. But at the x equals c value, where it equals 0, you have a vertical asymptote. Right? It's all about where does the denominator equal 0. So if you're taking a look at this function, the question eventually you're asking yourself is where the denominator equals 0. But what you have to keep in mind is that other things can happen when the denominator equals 0 as well. What other thing have we already encountered that could happen if the denominator equals 0? Could get a hole. So if you simply look at this equation and you set the denominator equal to 0 and tell me both of those are asymptotes, you may or may not be right. Right? You may also be telling me something about a hole. So how are we going to distinguish the difference? You could graph it. I think factoring is probably your better bet in terms of speed of doing things and maybe even accuracy, because sometimes graphs are not all that accurate in terms of the actual values we're looking for. So let's give it a try on the factoring. We have to factor both the top and the bottom, right? So numerator, how will that numerator factor? Good. Do you remember the special form that is taking on? What it's called? Difference of squares. You're close. Yeah, it's called difference of squares. So that's a difference of squares formula. How about the denominator? What in the world will it factor into? X plus 1 and x minus 3. Remember, you're checking to make sure that the inside term equals -2, and it will if you factor it this way. So what do you see happen? Yeah, these match, right? So that is not going to give me an asymptote. That factor will not give me an asymptote. It will create a hole in the graph at x equal 3. We'll talk about a little bit more about that in a minute. But we do get an asymptote. What is my asymptote for this? Okay, so everyone that said it said the right number, but you didn't say the equation of the asymptote. I'm missing a y, aren't I? It looks like an R. When they updated the operating system for these iPad minis, they became so large and took up so much space inside of the iPad that it delays my writing. So every time you see me erase something and rewrite, it's because I'm faster than the iPad. Isn't that fun? It's not fun actually at all. All right, so here's my asymptote. It's spelled right now, right? Asymptote, good. Okay, so what is my asymptote? It's actually an equation. What's the equation of the line of the asymptote?
X.
Yeah, x equals -1. So if you tell me that the asymptote is -1, you've got a problem. Because -1 is a number, and asymptotes are lines. You guys with me? And you might feel like, well, that's being a little bit picky, but the problem is there are also asymptotes that occur that are horizontal, and they say y equals. And we will get to them eventually, but we want to be clear that which one we're talking about. So this is x equal -1. Okay, we're going to take a look and talk about the same kind of an idea on this problem. It says to determine whether the graph of the function has a vertical asymptote or a removable discontinuity. Do you know what this phrase removable discontinuity means? Okay, it's easier than that even. What does it physically look like to have a removable discontinuity? A hole. This is a fancy way of saying hole. Okay, so this is asking, is it an asymptote or is it a hole? So it's much like the same question that we had over here. It's just phrased a little bit differently. That's all it's doing. So taking a look at this one, they actually tell you that the point that they're concerned about is x equal -1. So what happens to x equal -1 on this graph? Do we have an asymptote or do we have a hole? How do you know we have an asymptote?
Because you
Okay, did you guys catch that? You can't factor that numerator, right? What if the numerator said x squared minus 1? Then you would be able to, but it's x squared plus 1, and that plus 1 makes it unfactorable. All right, so this one can't factor. So it's that we will have an asymptote. And I would likely ask if it were on a test how you know. Okay, so I'm going to write that down for the sake of doing it right now, just so that you remind yourself and are aware as you take a look back at this hopefully later. This is because the numerator doesn't factor to reduce with the denominator. Since it doesn't reduce, we will not have a removable discontinuity. We will have an asymptote. All right, some properties of infinite limits. C and L are real numbers. F and G are functions. The limit of f of x as x approaches c is infinity, and the limit of g of x as x approaches c is L. It's actually got a numerical value. These look a lot like the limits you've seen before. It's just an extension to include the possibility that one of the limits is infinity. Notice what it doesn't say. It doesn't say they're both infinity, right? It doesn't say f of x is infinity and g of x is infinity. Weird things happen when there's two infinities involved. I know that sounds sort of strange, but take a look and I'll give you an example why. All right, so the sum and difference, they look like they should, right? So if you take the limit of f of x plus or minus g of x, right, that one of them is infinity, the other one's a number. So what happens when you take infinity plus or minus a number? It's still infinity. Okay. Now what happens when you take infinity times a number? It's a non-zero number. Did I have that condition in there somewhere? L, yeah, L is greater than or less than 0, actually, it's in there. Two conditions. So if L is greater than 0, it's a positive infinity. If L is less than 0, it's negative infinity. Notice it doesn't say what happens when L is equal to 0. There's a reason for that. We like to say 0 times any number is 0, and that's true, but infinity is not a number. Sometimes when you multiply something infinite by 0, it's 0. Sometimes it's infinite. And sometimes it's the number 2, or 1, or square root of 87. I don't know, whatever. You can get anything you want when there's 0 times infinity involved. Okay. The quotient one, again, it matters the order of this. Notice, the value on top is the limit that we know a number for, right? It's L. One on bottom is infinity. So if you divide something that's a constant number, or it's approaching a constant number, by something that's approaching infinity, you get 0. So sometimes in our minds we might say something like 1 divided by infinity is 0. We don't really divide by infinity, but that's sort of what our mind is thinking about as we're trying to process that. Okay. Again, also noticing you don't see infinity divided by infinity. Again, sometimes that's infinity. It could be 0, it could be 1, or 8, something like that. All right, so let me give you an example of how each of them fail. We have a little time to do that, so this will be a good place to do this. All right, so we're going to do the first one, and we're going to presume that they're both infinite limits. Okay, we've got something going on that's infinity. Okay, so I need a C value to make that happen. I need to figure out what to do to get that to work out. Now, if f of x and g of x were actually the same thing, and you subtracted them, even though they were both infinite, right? What happens when you track something that's exactly the same function from itself? It equals 0. So a good example of the first one failing would be if we had the limit, or if we considered the function where the limit approaches x approaches 0 of 1 over x. Okay? This would be infinity or negative infinity, depending on if we're approaching one from the left or from the right. Let's approach from the right, and then it'll be infinity. So if we had this so our function f of x equaled 1 over x, and g of x also equaled 1 over x, well, when I subtract 1 over x minus 1 over x, I get 0. I don't have any problem with infinities, right? I get 0. You could do the same thing for addition. You would just need one of the functions to be 1 over x, and the other function could be what if you were adding it? Negative 1 over x. Right, so on this first one, if you did f of x minus g of x, you get 0. The second one, f of x minus plus g of x, and it equals 0. Okay, well that's not what that definition said I would get if I had one of them infinite and the other one finite. So I gave you some examples where it sort of didn't fit the criterion, but it could fit the criterion. What if you had f of x equal to 1 over x and g of x equal to 1 over x squared? Those both have these asymptotes at x equals 0, right? When I subtract these, whoops, I get 1 over x minus 1 over x squared, which I can combine. That's fine. It gives me x squared minus 1 over x squared. That's fine. Did I write that right? X minus 1 over x squared, sorry. But this still has an infinite limit because the denominator, the factor in the denominator is still there, right? I'd still have an asymptote at x equals 0. So this one's limit would actually still be in infinity. That does not look like an infinity. That's better. So different things can happen, right? I gave you an example where it actually fit and an example where it actually didn't. You can do the same sort of things when you're looking at the product one. Okay, so again, we could use 1 over x. That's fine. But we could also use something else that has a value where we're approaching 0 and it doesn't work, like 1 over x squared. Well, what happens when I multiply 1 over x times 1 over x squared? I get 1 over x cubed. It's still infinity. That's fine. But what if I use something where it ended up canceling that x out somehow? It wouldn't work. I'd still get it. I could actually get a whole number value. The quotient one is really interesting. If you were to do something where it divided out the problem, right? It divided out the problem spot, the asymptote, that denominator. It canceled somehow. You could actually end up with any number you want, right? It's like saying, what happens if I had 2x over x? It doesn't fit exactly my description, but the x's would cancel, correct? Okay, same thing happens. So like if g of x and f of x were the same thing, they would divide to the number 1. But if g of x was 3 times what f of x is, they'll divide to the number 3. Right? So like if I had, I'm not going to write it down, but if I had 1 over x down here as f of x, and I had 3 over x as g of x. Yeah? That would divide to 3. So I could pick any number I want. It wouldn't have to always be 0. Or if I had 1 over x squared divided by 1 over x, I would have an infinite limit still. It would still be infinity. So the conditions are really important the way that they're set up. One is the limit, has a limit that approaches infinity, and the other one has a limit that approaches a constant value. All right, we've got one more example. This says find the one-sided limit. I don't know why it says find twice. So say find the one-sided limit if it exists, This is the limit as x approaches 2 from the left of x squared over x squared minus 4. We did a graph the last time we found one, so I'm going to do a table on this one, okay? Just to remind you that you have that option as well. So if I were doing a table for this, and my x values are supposed to approach 2 from the left, what might my x values look like? What would be a number that is approaching 2, but from the left-hand side? 1.9. Thank you, Marco. 1.9. Now you guys are rolling. What's the next one? Yeah, 1.99. And a third one would be 1.999. Again, you don't have to do this with a number chart. You could do it with a graph. It'd be okay. But I just want to show you another option just to remind you. And then this one would be, well, it'll be y1 in your calculator. We put this in as y1, right? All right, so if I put in 1.9 into this equation, what do I get? We'll go with 3 or 4 decimals, something like that. Whatever your screen is showing you when it does it is fine for me. It says something. What's it say? Okay, did everybody's calculator give them that? Okay, anybody's not? Okay, good. How about the second one?
-99.
And the third one? So obviously there are more decimals. It's just truncating it, right? It's shortening it for your screen. This is sufficient to see what's happening, though, right? It's going to what? Infinity or negative infinity? You got it, yeah. So this one, as we go down this table, is approaching negative infinity. So this limit the limit for this is actually negative infinity. That is the one-sided limit. And it matters, you got to put the right side. If you did 2 from the positive side, it may or may not be negative infinity. This one actually would be. It wouldn't have changed it because all of my x values that are in my equation are squared. So it doesn't matter if I put in positives or negatives, I'm still going to get something that's going to be the same value. But most functions, the signs do actually have some impact on them. Okay? Any questions on this one? All right.